Hey guys, let's talk about normal distributions. So, a normally distributed set of data is going to be continuous data that is mostly centered around the mean and symmetrical in manner. Probability distributions, the continuous ones, they come from a family of functions that look like this. We have f of x is equal to 1 over theta times the square root of 2 pi e all raised to the negative 1/2 times x minus mu over the standard deviation squared, okay? So the shape of the distribution is going to be dependent upon the standard deviation and the mean. If you graph this function, it will look like this. And it will change depending on the mean and standard deviation of the continuous one variable data set that you are talking about. So like let's say the data was gathered really closely about the mean, it would look like that. Spread out, it would look like that. And this curve would generate that. If you were to find the area under this curve with integrals, we'll learn about those later in the year, you would find that the area under the curve of this family of functions is 1, which makes sense because if you add up all the probabilities in a distribution, they always add up to 1. So that's the connection between the math and the normal distribution that we are pretty clear with at this point in the game. So the normal distribution, it tells us what percentage of the population lies between certain values, right? We know that within one standard deviation of the mean, we got 68% of the data. Within 2 standard deviations of the mean, we have 95% of the data. And within 3 standard deviations of the mean, we have 99.7% of the data. Okay, so we can use our knowledge of normal distributions in order to kind of find some other bounds, right? What percentage of the data is in between x1 and x2? We can use our knowledge of normal distributions to find something like that. There is a thing in our calculator, right? And he is called the normal CDF function, okay? So go ahead and write down normal CDF. And we use the normal CDF function to calculate unknown areas or probabilities under the curve. So as soon as you can get this down, the better off you will be. Area under the curve is the same thing as a given probability. Okay, so we can use the normal CDF function when we know the mean, the standard deviation, and the bounds, or the data points along the x-axis that this thing is bound between, right? This data point and this data point, something like that. Okay. So the way that you find this is you go menu 552, and that will pull up the normal CDF function for you. Okay, so let's write that down. Menu 552. Okay. And let's say we have a normal curve that looks like this. Here's the mean. And we want to find the area under the curve, or the probability that we will select a score that is less than 2.7 of some kind of data, some kind of continuous data. We're trying to find this unknown area over here, and we're going to use a normal CDF function to do that, okay? So what is the limit to this side? Well, a normal distribution curve is asymptotic to the x-axis, right? So as we head out in the left direction towards infinity, the graph keeps on going and going and going and going and never quite approaches. And never quite hits, but always approaches the x-axis, okay? So essentially, our lower bound towards the left is negative infinity. And then our upper bound to the right is 2.7. So think about it as like identifying the bounds. The lower bound is going to be negative infinity. You can type that in your calculator as, oh, dang, it's already in there. Negative 9. E is, remember, scientific notation, times 10 to the 999 is kind of like what this says, right? That's our lower bound. And then our upper bound is going to be 2.7. So we would enter this into the calculator, right? Our upper bound is 2.7. Our mean is, well, we need a mean here. So I don't know, let's just make it up. Or we could just use the standard normal distribution. That's totally fine. We can have our mean as 0 and our standard deviation as 1. Let's see. So our calculator says that 0.996 is the probability that we will choose a data point that's less than 2.7 here. Okay. So let's think about our curves, right? You always want to step one, sketch the curve that you're trying to show, right? So let's say you're given a curve that looks like this. We have our mean here, 85. And we're trying to find the probability that something is greater than 85. Someone's score on a test is greater than 85. Well, if we were going to type this into normal CDF, right, our lower bound would be 85, and our upper bound would be infinity. Okay. And then there's another way that you could see normal CDF used, and that is if we are bound between two scores, right? So let's say we're bound between -2 and 2, and we're trying to find the area between these two data points, or the probability that you would select an area between those two data points. And then your lower bound would be -2, and our upper bound would be 2. So with the normal CDF function, or just trying to find an unknown area, you just have to kind of be able to identify the lower bound and the upper bound by drawing a picture, and then you just input that into the calculator. That's it. Okay. Now let's talk about if we are given an area, but we're trying to find the X data point that corresponds to that area, right? This is called the inverse norm function. It's the opposite of what you just did pretty much, right? That makes sense. So this is the inverse norm function. And the way you can remember this, or the way that I remember this is when we have a known area, and like norm, known, they kind of sound similar. I don't know. Right? We use this when we know. Get it? Know, inverse norm. When we know the mean, the standard deviation, and the probability, or area from the left. And underline left, that's important. We're going to talk about it in a second. Okay. So let's say we have a picture that looks like this, right? And they're like, okay, we want to find at what data point 85% of the data is below that data point. Okay. We are given the area on the left, or the cumulative area from the left. That's great. Our inverse norm function loves that. We would just type it in really easily on our calculator. Inverse norm 0.85. The mean is something. The standard deviation is something. We're good to go. Let's say the mean is 10 and the standard deviation is 4. The way you would enter this into the calculator, right? You would do menu 5, 5, 3. Okay. You type in the area, you type in the mean, type in the standard deviation, and it will give you this X data point here, 14.1457. Okay. So it gives you the X data point of the boundary. And notice when we're given the area from the left, we are good to go. Area from left, good to go. If we're given the area from the right, we just have to do a little bit of thinking, but that's okay because we are good thinkers. So I have maybe this picture given, right? Same mean is 10, standard deviation is 4. Except now we want to find, or we're given that 15% of the data is above the data point X. What is that data point X? Well, CDF is going to be a cumulative density function, right? So it only accumulates area from the left of the curve, right? Think about it. As we're reading from left to right along the x-axis, that's where it's acquiring its area. That's where it's accumulating its area. So if we're given an area on the right, then we are going to need to do 1 minus the area on the left. Okay, so if given area on the right, if given area on the right, you have to enter it into your calculator like this. You would do inverse norm, 1 minus the given area, which is 0.15, and then you would put in your mean and your standard deviation. Okay. So I'm going to go ahead and just like copy this and then change this guy because now we have the area from the left. Oh, dang, I picked numbers that are literally the same. Well, that's okay. 1 minus 0.15, and you would get the exact same number because 1 minus 0.15 happens to be 0.85. I should have picked a different number. Hey, what are you going to do? All right, so this x boundary here is 14.1457. Okay. If any of this is like way too fast or you're like, literally, what's going on? That's okay. We're going to go over it in class a lot more. I just wanted to give you a preview and a lot of the notes so that way we can spend time in class like doing the problems and not just passively getting the notes. Okay. This is just a nice little visual that kind of summarizes when we use the two calculator functions that we just talked about, normal CDF and inverse norm. This one we're going to talk about more in class. This is when we standardize to go from a normal distribution to the standard normal distribution, which is where we have a mean of 0 and a standard deviation of 1. Use the standard normal distribution. Think about him as like one of the children of the normal distribution family, right? We have two happy normal distribution curves, and they had a baby, the standard normal distribution curve. Okay. So normal CDF is when you are trying to find the probability or area. Inverse norm is when you are given the area and you need to find the x value or boundary that satisfies the question. Okay. So go ahead and pause the video and try example 1 and example 2 with the pictures that I gave you.